It has long fascinated those of us here on Earth. It's part of our human myths and legends. For tens of thousands of years, we've looked at this neighboring planet and wondered, is it like Earth? Is there life on Mars? Hi, I'm Bob Ballard. Scientists are finally beginning to crack the secrets of Mars. While we have no human footprints yet on Martian soil, we do have eyes there. Satellites and rovers are giving us close-up looks at this mythical red planet. Scientists are now answering many questions about Mars, but they are also finding new mysteries, new challenges to what we thought we knew. So get ready for liftoff. This is Jason Expedition, Mysteries of Earth and Mars.
From space, Earth and Mars couldn't look more different. Our planet is third from the Sun, a blue world of liquid water. Mars is the fourth rock from the Sun. Half the diameter of Earth, it's a cold, dusty outpost in our solar system. Yet these two planets share a history that started about 4.6 billion years ago. They were both born out of matter swirling and colliding in space. As they cooled, both formed crusts. They both erupted with volcanoes, and their surfaces were pelted with meteorites. For about the first billion years, Mars and Earth were probably very much alike. We look at Mars today and see where water once carved its surface. We see dunes and volcanoes, things we have right here on Earth. But something happened. Scientists want to know what and why.
This is our sister planet. This is supposed to be like Earth. What happened there?
Seeing things on Mars makes us kind of look at our own planet from a different angle, and we learn things about the Earth that we might not have learned.
Trying to understand the evolution of the Earth is really important.
Mars offers us a new vantage point on planet Earth. Because Mars was born at the same time, and yet it grew up different. It may have had life, it may not, we can't tell, but we're looking.
Ultimately, all of this is embedded in the big question, are we alone in the cosmos?
Our best chance of being able to know that, at least in our lifetimes, is on Mars.
And I think that's what drives Mars exploration more than anything right now. Yeah, we want to learn a lot of other things, but life is the central issue.
So join our Jason researchers as they build the technology, study the data, and unlock the mysteries of our rocky neighbor, the red planet, Mars. Tracy Drain is a NASA engineer. She's a member of a team that not only designs the technology, but figures out how to get that technology to Mars and keep it in touch with Earthbound scientists. In order to do that, she has to understand some basic laws about movement and gravity.
Gravity is an attractive force between two bodies. Anything that has mass pulls on anything else that has mass, and that's what gravity is.
A mathematician named Sir Isaac Newton figured this all out back in the 1600s. Newton said the force of gravity partly depends on the distance between two things. If they're closer together, the force is stronger. Further away, it's weaker. It also depends on something called mass. It's easiest to think of mass as the weight of something, but that's not entirely true.
Okay, mass is different from weight because mass is related to how much stuff is in something. Like how many atoms are in my body determine what the mass is. And that's the same no matter where I am, if I'm floating around in space, if I'm on the Earth. But weight is a measure of, say, on the Earth, how much the Earth is pulling on me. Mars is smaller, so it's going to pull on me less. It has about a third less gravity of the Earth. So though I weigh about 135 pounds on the Earth, I'd only weigh about 45 pounds on Mars.
So, you have this thing called gravity throughout the universe. And if you want to blast off from Earth and go to Mars, you have to deal with it. That means you have to understand some more of Isaac Newton's ideas. The most important are three laws that describe motion.
Newton's first law basically says that an object in motion will remain in motion and an object at rest will remain in rest.
So a thing that's just sitting there will sit there until a force makes it move. Once it's moving, a thing will keep moving at the same speed in a straight line forever. Forever, that is, unless another force, such as gravity or friction or a collision with another object, changes its speed or direction. So, that's Newton's first law. Newton's second law is critical to any rocket launch.
And Newton's second law is basically the equation that says F equals ma, and that means force is equal to mass times acceleration.
We've already talked about mass. It's kinda sorta related to how big and dense something is. Acceleration is what sports cars do when they go from 0 to 60 miles an hour in 3 seconds. Using force equals mass times acceleration, you can figure out how much force it takes to accelerate a rocket and launch it toward Mars. That brings us to Newton's third law of motion. It says when things go zipping around exerting forces, there are consequences. Simply put, Newton's third law says for every action, there is an equal and opposite reaction.
If you're two people standing in an ice rink and you push the other person, they're going to take off in one direction and you'll take off in the other direction because this force has caused an equal and opposite reaction between the two of you.
So, let's take what we know about Newton's laws and send a spacecraft to Mars. Say we have a rocket, ready for liftoff. First, we're going to get it off the ground, using Newton's third law.
In order for a launch vehicle to be able to get off the surface and travel, it produces a thrust by lighting its engines and firing downward in order to send the launch vehicle up.
So the engines fire one direction and the rocket goes the opposite direction. Equal and opposite reactions. But before we get to this step, we have to figure out how much force it takes to lift the rocket away from Earth's gravity. Remember, force equals mass times acceleration?
The amount of force, of thrust that you need is related to the mass of your rocket. But you have to keep in mind that if your spacecraft is more and more and more massive, that requires more and more and more thrust from your launch vehicle. And you also have to keep in mind how much acceleration you need. You need at least enough acceleration to overcome the pull of the Earth, plus enough to get to the velocity you need to escape from the Earth's pull and to get where you're going.
Once your spacecraft gets to Mars, you also have to figure out how to put it into orbit around the planet. You have to use gravity to do that.
So we have to do what we call a Mars orbit insertion. Once you're on your trajectory to Mars, you don't want to slingshot on past, so you fire your thrusters to get you closer in, and then the planet's gravity sort of captures you. And you can imagine it as feeling the gravity like having a ball on a string. When you're twirling it around, the string keeps the ball attached in orbit, and gravity acts like that string for us. And you have to get close enough so that you're on the string so that you can be in orbit. Newton's laws of motion are key to planning and executing interplanetary missions. All of those complex equations and designs are really based on those laws of motion.
Of course, there's one more thing you need to know if you really want to be a rocket scientist, or any scientist. That's math.
I think I've heard a quote that I really liked saying the reason we landed people on the moon is because those guys understood calculus. I mean, you have to have the math down, or else you don't know how much thrust you need to get the launch vehicle off the ground. You don't know how much thrust you need to change your velocity in order to get in orbit around Mars. It's critical to everything.
Expedition Field Notes by Katie Keller. Location, Jet Propulsion Laboratory, Pasadena, California. My research, engineering for space. I'm at the Jet Propulsion Laboratory with engineer Kobe Boykins. Kobe is part of the team that designed and built the Mars rovers Opportunity and Spirit. We're about to look at what it takes to build something lightweight, yet durable enough for space travel.
So Kobe, why is it important to make spacecraft lightweight?
Well, the reason it's important to make spacecraft lightweight is because we're going to launch this stuff to space. And the less mass that you have, the less force of gravity you feel pulling on you as you launch. So the lighter you are, the easier it is to get into space.
How do you make spacecraft lightweight?
Well, one of the things we do, or a couple things we do, sometimes we use different materials, alloys, composites. The other thing we do is we actually try to shrink everything inside. So what I have here is an example of some actuators. We use the word actuator to mean a motor plus a gearbox. And what I have is, this is the outside of the gearbox. This is made out of steel. And inside we have all these little gears. What this is doing is it's actually taking the output, which is from the motor, which spins very, very rapidly. We can hook this up and we can watch it rotate. So the motor is turning, and that's turning a set of gears. And what we do is we slow the RPMs down, but we increase the output. So when we put the actuator in here and start to spin the gears, you can see that the gears close to the motor go really, really fast. You have small gears to big gears, and then small gears to big gears. Each time you do that, you're actually slowing down the output. See how it's spinning very, very slowly? So what we're doing is we're slowing down the output of the motor and getting a lot more force. And that's going to turn something like, let's say, a wheel for the rovers per se. It's very similar to what happens on a bicycle. When you're on a bicycle, you're inputting power. Your body is spinning pretty rapidly. We gear it so that you can actually spin the output even faster. So it's almost a reverse motor in terms of a bicycle, because you're pedaling actually pretty slow, but the back wheel is going really, really fast. One of the actuators that we had on the rover, the one that opened the actual lander pedals, 33,000 inch-pounds. Enough to pull over a building. It just happens really, really, really slow.
All right, Kobe, you already talked about one way to reduce the weight, which was to actually shrink the size of the components of what you would put into a spacecraft. What would be another way?
So some of the other things that we do is we choose materials, composites. Composites are things that we use every day. Cardboard, styrofoam. I have a little example of what a composite is that we would use for space. What we can do with this is we can make something that's really lightweight and it has a lot of strength. To try to bend it, just try to bend it from side to side. It's really, really strong, really stiff.
A lot of the main body parts of the rovers were built of lightweight composites. Another way to save weight is by using mixtures of metals called alloys. Alloys can be very different from the original metals that are in them. Kobe introduced me to an alloy called nitinol.
One of the interesting properties about nitinol is that it has the ability to retain its shape. It has a memory. And we'll train it to go to a different shape. So let's go ahead and try that. And we're going to take it over the flame, and we're going to actually try to coil it up. Okay. Now what I want you to do is I'm going to let go, and I'm going to let you dunk it in the cold water here. Oops. Okay. So now what we've done is we're training it to be in a coil. Go ahead and pull it out, and let's straighten it out. So we'll straighten the coil out. Now when you dump it back in the hot water, it should go to a coil. So let's see what happens.
That's really cool.
This is one of the things that I said, we can use this as an actuator. Let's talk about, let's say, like a windshield wiper. Let's take solar rays. They accumulate dust, and maybe it's possible to actually wipe off the dust. And if we could do that for very, very lightweight, it would be really worth it.
All of the materials, engineering, chemistry, and physics behind the rovers came together here, a clean room at JPL.
As we come over here, now we're looking at what is actually the deployed rover.
This is where Kobe and the rover team saw years of designs, tests, and more tests turn into a reality.
And you've done all the math that you can and said, the probability of success is 99.9999, and okay, let's go.
And liftoff of the
These are like children to the people that worked on them and the people that had science instruments on them. They're beings that are giving us a window into what Mars is today. I mean, I'm sitting here as a person that's actually sent something to Mars. In my wildest dreams as a kid, I wouldn't have been able to say, I'm going to send something to Mars. I may have wanted to do that. The reality is that that's probably not going to happen. But, oh my goodness, I sit there and I go, wow, I was a part of that. A kid in Nebraska, How would I end up here?
Missions to Mars have largely concentrated on the planet's geology, and there's a good reason for that.
Planets like Earth and Mars are made of rock. So the rocks of a planet are the record books, if you will, the history books that we need to read. And we need to read them at not only the scale of a rock in my hand, but also at the scale of the landscape. Landscapes are features on surfaces that are formed by specific processes, and they reflect the histories of planets.
The planets in our solar system all formed around the same time. Both Earth and Mars formed when chunks of matter, drawn toward the gravity of the Sun, collided with each other. Eventually, enough matter collided that it created its own gravitational field and formed into spheres. These became the planets Earth and Mars.
Earth and Mars were formed at the same time around 4.6 billion years ago. Perhaps the first billion years of the histories of these two marvelous planets were very similar. But then they started to diverge. The intensity of the geologic processes that shape the crusts, the surface of these planets, started to differ. Earth's crust was organized at that point into things we call tectonic plates. On Mars, we think the planet never had enough energy to produce a thin-skinned crustal plate motion like we have on Earth. Instead of having lots of boundaries and things, Mars appears to be organized as one big thing, one big continental plate, on which other things poke through and occasionally rip apart. It's a fundamental difference.
Because the Martian crust is one big plate with limited movement, the surface of Mars hasn't changed as much as Earth's. On our planet, the surface is constantly changing. That's because Earth's crust is broken into chunks geologists call tectonic plates. They float on the mantle, a layer of molten rock which surrounds Earth's superheated core. The floating tectonic plates collide. They dive over each other and under each other. They pull apart and push together. They create cracks and vents and volcanoes in Earth's crust. And when the plates move, the Earth does some amazing stuff. It releases gases and heat. It melts down old rock. It spits out recycled rock. It transforms landscapes and life.
The activity of plate tectonics on Earth actually has affected the chemistry of our atmosphere. This is vital to the health of planet Earth. That system produces the energy for life, drives ocean circulation. This is the plate tectonic system that distinguishes the Earth, as far as we can tell now, from the other rocky planets in our solar system, in particular Mars.
Other features on Mars are very Earth-like. Mars has canyons, dunes, ice caps. It has volcanoes. It even has river valleys. But on Mars, these landscapes hold a few differences and mysteries.
Mars has beautiful river valley systems, and yet the ones on Mars are organized a little bit differently. They don't have as many little channels coming into them, suggesting that whatever water flows into them is not organized in quite the same way as on Earth. Mars, at almost all scales we look, we see fields of sand dunes. Then they come at all scales, almost everywhere. In the floors of canyons, around volcanoes, we find fields of dunes. On Mars, they're everywhere, and on Earth, they're localized. Again, reflecting differences. Then there are the impact craters. Impact craters, scars of cosmic collisions, and these reflect the long history of these cosmic collisions. Perhaps one of the most exciting things, though, that we've recently recognized is the existence and occurrence of hillside gullies on Mars. Liquid water, we think, is exchanged from the very shallow surface, a few hundred feet deep, erupting onto hillsides, producing gullies. The water cycle on Mars may change from a frozen, dry, underground system to a near-surface, warm, wet one.
Of all the mysteries scientists hope to answer, the biggest is there life, or was there life on Mars? Geologists help pinpoint where on Mars to investigate that question. Life needs liquid water. So, explore those places that look eroded and shaped by the action of water. So far, scientists know Mars had salty lakes, maybe oceans. They know the ice caps are frozen water. The next step is to see if any liquid water remains.
One of the big enigmas about Mars, questions, is there liquid water as a liquid in the areas underneath the present polar ice caps? But for me, I think the realization that there is at least what we would call a modern water cycle on this planet has really caught my attention, caught my fancy. We see the gullied hillsides. We see the possibility that it once rained. So Mars is a water planet. It's just hiding its secrets about water. And that to me means water, good environments for life, put the two and two together. This planet must have been alive, and we just have to figure out how. And maybe it still is.
Expedition Field Notes by Mitchell Graves. Location, Death Valley, California. My research, reading the rocks. Vicki Hamilton is a planetary geologist from the University of Hawaii. Vicki studies meteorites from Mars, but today we're studying rocks and landscapes in Death Valley. Death Valley has many landscapes similar to those on Mars. Scientists use these landscapes as analogs or real-life models of the red planet. What they find here helps them understand Martian landscapes.
We can't send geologists to Mars right now, so the easiest thing to do is to look at what we see and compare it to features that we know on Earth and can go and see on Earth in person.
Vicki and I are about to read the landscape in Death Valley. Our first step is learning to identify different types of rocks and the processes that made them.
There are thousands of kinds of rocks, but what we can do is break them down into three basic groups. We have igneous rocks that are formed from magmas, usually we think of those as coming out of volcanoes. There are sedimentary rocks that are just pieces of other rock that have been fused together. Or they can be rocks that are chemically generated, usually by precipitating chemicals out of water. And then there's a third kind called metamorphic. And metamorphic rocks are either sedimentary rocks or igneous rocks that have experienced a lot of temperature or pressure, that changes them into a new kind of rock.
So out of those three you just named, do we find all three on Mars?
Well, it's a really great question. We haven't seen any indication of metamorphic rocks on Mars. Either they're not there or we can't see them. So now if we take a look around us here, what do you think that white stuff might be?
Looks like salt from here. Like a salt valley almost.
Okay, well, if we want to figure that out, we should really go take a closer look at it, shouldn't we?
Yeah, let's go.
Okay.
Once geologists identify a rock, they have a general idea of how it was made. The next step is to read the landscape, or in this case, taste it.
Okay, so let's give it a taste test.
Pick a little piece out.
Pretty salty, huh?
Definitely salt.
So this is salt. You're right, and it forms by evaporation. There's chemicals in the water that come down into this valley, and when the water evaporates, the salt gets left behind. And so in terms of what's happening on Mars, we think exactly the same kind of process could happen. We see plenty of evidence for past water on Mars, and so there's no reason to think that we couldn't have possibly formed salt minerals as well.
Since scientists can't walk on Mars, not yet anyway, they use photographs and other tools to study Martian rocks. One important tool is a spectrometer. It measures energy waves in the electromagnetic spectrum.
The EM spectrum is all of the light that is out there around us all of the time, and sometimes we think of a spectrum as the ability to break down light into different colors, but there are a whole range of colors outside of those colors that our eyes can see, and those other colors have different energies. The very high energy waves, we have things like gamma rays and X-rays, then ultraviolet, and then we have the visible light that our eyes can see. And then as the waves get longer, they become infrared light, and then we move out into microwaves and radio waves.
Our spectrometer measures visible and near-infrared parts of the spectrum. A similar tool helps scientists see the colors of Martian rocks.
While you and I can sit here and hold these rocks, we can see that they have colors. But if we were up in space looking down on Mars, we wouldn't be able to see the colors of the rocks. So what we can do is carry a spectrometer on our spacecraft and use it to look down, and then we can figure out that there are red rocks and green rocks and dark rocks. There are other parts of the electromagnetic spectrum that we can use to understand what the rocks are actually made out of.
The last stop is a big hole in the ground. Vicki tests my powers of observation.
What do you notice when you look across that far wall?
I see a lot of oranges, looks like erosion. A lot of dark layered areas at the top.
There's also this big hole here. And so what do you think might be some ways to form something like that?
Well, when you say crater, I think of a meteorite impact, some volcanoes that I've seen around the world.
Yeah, that's great. That's exactly it. Either an impact crater or some kind of volcanic crater is probably the two best ideas for how you'd form this feature. So what we'll do is we want to get spectrometer measurements on both kinds of rock, or both kinds of sediment, really. Both of these are sediments coming down from these rocks.
At the base, we collect spectra for both the dark and lighter colored sediments. But we find more immediate answers by doing a little hands-on. The lighter colored sediment eroded from the lighter colored rocks in the crater walls. It is very powdery.
The tan rocks on the bottom are made of this mud material that was probably deposited by water sometime or in water. Those are sort of fine-grained sedimentary rocks. Now if we look at this is a completely different kind of texture. It's a completely different kind of material. Those little holes are called vesicles. And vesicles, are formed in volcanic rocks. And what they are is little places where gas was trapped in the magma when it was hot. And then the gas escapes and it leaves a little hole behind. So now that we've established that this is a volcanic rock and that the gray rocks on top are the volcanic rocks and that they're sitting on top of sedimentary rocks, when you talked about the two different ways that this hole in the ground might have formed, I think we can pretty safely say that there was a volcanic process involved.
Okay, yeah, because you have the volcanic rock and then you have the different layers. And you get a lot of these darker rocks on top of the older, oranger rocks.
Yeah. So the question then is, do we have rocks like these at Mars? And we probably have both kinds of rocks. We probably have sedimentary rocks, but then there's also a lot of just igneous rock on Mars, and it may be overlying the sedimentary rock, just like what we see here.
And while Vicky uses geology to study Mars, anybody can get to know our own planet the same way.
You can easily go out in your backyard or into the local park or, anywhere and pick up different kinds of rocks and categorize them by their shape or their color, or figure out, how they're similar or different from other rocks from a different place. And that's very much a part of kind of what my job is all about, and being able to walk outside and know something about how the Earth worked, I just found really fascinating.
NASA's research follows the water on the Martian landscape. The reason is simple. If there is evidence of water, it's the most likely place to find evidence of life. But how do scientists prove life exists, or did exist, in a world of red dust and cold rock?
We live on a planet where we know it's been populated with life for over 4 billion years, and yet we go into old rocks and we try to look for signs of that life in environments where we know the life was present. It's darn hard to find, something that you can really point at it and say for sure, this was a signature of life.
One mystery from Mars brought the difficulty of finding extraterrestrial life into the headlines. It was a meteorite found in Antarctica. Scientists determined it originated on Mars. Then they found microscopic forms and chemical traces that could be remains of life. And they could be, but they are just as easily the result of inorganic processes, chemical reactions that have nothing to do with living things.
And it just shows the problems that you can come up against, because a lot of inorganic processes mimic the processes of life, and you have to be very careful about dividing between different lines of evidence to make sure that you really get it right.
So scientists are on the hunt for the kind of evidence that could only result from living things. To do that, they have to understand the history, chemistry, and possible environments for life on Earth, then apply that to Mars. For starters, there are certain things life needs.
To get life, we need building blocks. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur are the main ones. Those are found all through the cosmos. So why no life? Why can't you get life everywhere? And that's because you have other requirements. You need liquid water to be present, and you need to have a way to make a living getting energy from the environment.
Scientists think early in Martian history, the planet was more Earth-like. It had streams, standing water, and salty lakes, possibly oceans. Mars stayed that way for maybe 1 billion years. On Earth, 1 billion years was enough time for life to make an appearance. If Mars and Earth shared similar environments, they could have shared similar forms of early life.
So I think that what we're looking for is what was present on Earth from almost the very beginning of our planet's history, microbial life and the signatures of microbial life.
Microbes are tiny living things, organisms that changed this planet forever, making Earth a living Earth. The earliest were probably bacteria. They made possible all of the life we see around us today when they became photosynthetic.
Well, photosynthesis is this really cool invention that microbes came up with. They capture that energy from the sunlight in the presence of water, are able to form organic compounds and liberate oxygen.
For centuries, scientists believed photosynthesis was the basis for all life on Earth. But about 30 years ago, Jason founder Dr. Robert Ballard and a scientific team made an amazing discovery. Deep in the ocean, scientists found places where chemicals and heat escape from Earth's superheated interior. Called hydrothermal vents, they support thriving communities of life. This life is beyond the reach of sunlight, making photosynthesis impossible. Life here is based on chemosynthesis. This means microbes use chemicals as energy instead of the sun. Hydrothermal vents support a world of tube worms, clams, and species we have yet to find. The discovery of chemosynthetic communities changed where we look for life, and it opened the door to the possibility of life throughout the solar system.
The point is that when you're in these kinds of environments where you don't have sunlight available, there are all kinds of groups of bacteria that can nevertheless still make a good living. We think the early biosphere on Earth, and probably the early biosphere on Mars, and maybe even today in the subsurface, runs that way. It's all on chemosynthetic energy. We, on that basis, began to understand that there's a truly amazingly diverse biosphere of microbial life occupying a broad range of environmental conditions. In terms of temperature, we can go from well below freezing to the other extreme where we're living in hot springs, huge range of temperature. Salinity is the same thing. Organisms can live in fresh water. They can live all the way up to the point where salt crystallizes, about 300% dissolved solids. Acidity, that's the big one for me. pH 2, which will burn you because, it's acid solution and acid bath at high temperatures. In Yellowstone Park, you have these acid hot springs teeming with life. There seems to be no limit to the ability of life to adapt to extremes in the environment. And we're still discovering that. We don't know the full range. We find all these places now in the solar system where those environmental conditions seem to be within the possibilities for life. So where are the showstoppers? I don't think there are any. I think life could have well gotten started on Mars early in its history, and it could still be there today. It's just tremendously exciting. I can't imagine, anything more exciting than that.
Expedition Field Notes by Jeff May. Location, NASA Ames Research Center, Moffett Field, California. My research, finding signs of life. Linda Janke is a microbiologist with NASA at Ames Research Center.
My major job here, working for NASA, is to understand how life evolved here on our own planet, on Earth.
Linda studies the history of life on Earth and applies that knowledge to the search for life on other planets. Her big question, if life did at one time exist on Mars, what kind of traces did it leave behind? Scientists call those traces biosignatures. A biosignature is evidence that life is or was present. Dinosaur fossils, for instance, are a type of biosignature. But Linda doesn't expect to find dinosaur fossils on Mars.
No, I don't think dinosaur bones. But we're looking at fossils that can only be made by a biological organism.
Linda is looking for biosignatures that might be preserved in Martian rock. She's interested in tiny traces left by microorganisms. Bacteria, for instance, are microorganisms. But fossils or biosignatures from bacteria are hard to find. To find them, Linda studies the chemistry of bacteria. Then she tries to figure out what traces that chemistry might leave in Martian rocks.
We're looking at molecular fossils, a carbon structure of a molecule, a type of mineral that can only be made by a biological organism.
Wow, this stuff kind of looks like pond scum.
Well, this is a microbial mat.
We're about to study bacteria growing in what's called microbial mats. These mats were transplanted from a salt processing pond in Mexico. They grow in water that's really salty, what scientists call hypersaline. The water's similar to what probably existed on Mars.
Early Earth and Mars probably had a period of perhaps 1 billion years when they were fairly similar. We know that there was freestanding water on Mars, and we know it was hypersaline. Why don't we find out how saline the water is, Jeff? We have similar types of ecosystems here on Earth.
Looks like it says about 90.
All right, that's 90 parts per thousand. Normal seawater is 35 parts per thousand.
That's really salty then.
Yes, it's almost 3 times what our normal seawater is. Until very recently, that pond scum, or microbial mat, was the only form of life on this planet for billions of years. We believe that Mars had lakes or shallow oceans that were hypersaline, that there may have been similar communities. So we would like to understand the kinds of biosignatures that remain or are associated with a hypersaline environment.
These microbial mats are made up of layers. Each layer is a different type of bacteria, both living and dead. The thin upper layer is photosynthetic. It gets its energy from the sun and produces oxygen. An oxygen probe shows the lower layers are anaxic or anaerobic.
Anaerobic means life without oxygen. These are microbes that live without oxygen. In fact, they don't like oxygen. Oxygen will kill them.
So everything on this dark bottom half doesn't like oxygen and only this little teeny little strip at the top does?
That's right. That tiny little strip is providing all the energy that really fuels this entire mat. That's what we call a microbial ecosystem. Organisms have evolved to take advantage of every form of energy that's available. They depend on one another. This is a piece of frozen and then dried microbial mat. Bacteria that live in the lower layers use chemical forms of energy. Those chemical reactions and the energy from that initially starts at the surface of the photosynthetic mat. They live off of each other. They exchange different chemical compounds. Let's extract that now so that we can concentrate it.
In this chemical stew, Linda looks for signs that can only result from living organisms. Linda uses chromatography to separate and identify the combinations of chemicals found in microbial mats. Chromatography helps us see chemicals as colors. We've placed a concentration of pigment on a chromatography sheet.
And touch the plate.
A rainbow of colors soon appeared.
It separates by the compound, the type of compound, but the different compounds have different colors. And you see the darker band in your actual application spot? That's probably your chlorophyll. On Mars, we now realize that we could potentially be looking for the fossils left by these microorganisms. It's possible that there is present life also. I think it's very possible. That's one of the major jobs of the scientists here on this planet now, is to understand absolutely when we see something, is it life? Oh, look at that particle. It had to have been made by a bacterium. That will be an unbelievable day.